Hey class, this is going to be your 15.3 lecture. So 15.3 is mainly about conservative vector fields. And conservative vector fields we're going to see very shortly are just gradient fields. So that's not a big surprise. But we need to talk just a little bit about some classification of curves and regions first. This is going to come up both in 15.3 and in 15.4. So a curve is simple like these two if it doesn't cross itself at any point. And so it's not simple if it does cross itself one or more times. And a curve is closed if it starts and ends in the same place. So these are both closed curves, and these are not closed curves. We don't call them open curves, just not closed. They don't connect at the ends. Regions, we've got a couple of different properties on regions as well. We have connected and simply connected, and it is perhaps a flaw in the terminology that you do not have to be connected. A region doesn't have to be connected to be simply connected. So this kind of simply connected or connected and simply connected region, this is the ones that we'll deal with the most. We will occasionally deal with a region that's connected but not simply connected. These kinds of regions, they don't come up for us. If we needed something like this, we could, in some instances, like combine the regions and split, say, an integral over two regions or something like that. But essentially, we're going to be looking for curves that live inside a single region. So if we want a curve to be one continuous or contiguous, really, linear region, then we can't fit one of those inside two different connected regions. And if we only had one of these, we would just have a smaller connected region. So, so that's why we can kind of ignore these a lot of the time. So the definition of conservative is pretty simple. A vector field is conservative if it has a potential. In other words, if it is a gradient field. That's it. So a conservative vector field has a potential. It is a gradient field. So how can we test for this? If f is conservative, then by virtue of the fact that it is a gradient field, little f will be phi x, little g will be phi y, and if we've got a three-dimensional field, little h will be phi z. And then by virtue of Clairaut's theorem, right, phi xy equals phi yx. So fy, so here's f, take the derivative of that with respect to y, I get xy, phi xy. Here's g, so if I take the derivative of that with respect to x, I get phi yx, and Clairaut's theorem says those would have to be equal. And so this is going to be true for any conservative vector field that that fy equals gx, fz equals hx, and gz equals hy. I skipped those computations. Pause the video for a second if you want to double check and see why these would have to be equal. So those would have to be equal. And same for gz equals hy. So a quick example here. If f is e to the x cosine y, negative e to the x sine y, this is going to be a conservative vector field. And in order to see that, all we have to do is take fy, partial of f with respect to y, take the partial of g with respect to x. Those are two quick derivatives, partial derivatives if you want, and we see that those two functions are equal. So by our test, f is conservative. Just knowing it's conservative is nice, but usually when we know it's conservative, we're going to want the potential. So the potential here, we know that little f is equal to phi x. And that's e to the x cosine y. Well, that means that phi has to be one particular antiderivative of phi x. Actually, it could be a lot of different ones, but when we find a potential phi, we're going to find the one with, the easiest constants. So in this case, we take antiderivative of e to the x cosine y with respect to x, which is just e to the x cosine y. And then instead of getting an arbitrary constant, we get an arbitrary constant function. I know it sounds kind of weird to say, but I call it a constant function of y. In other words, this is a function that only depends on y. So it's constant with respect to x, because that's the variable we integrated with respect to. So phi could be e to the x cosine y plus y squared, or it might be plus 2, or whatever. We're going to figure out what these functions are in a minute. I do this differently than the book does, by the way. I just do a series of antiderivatives. Your book has a different process, and so maybe one of the other lecturers will go through that if you want to see it. So phi y is g, right? So g is negative e to the x sine y. So phi must be an antiderivative of phi y. Well, when I take the antiderivative of e to the x sine y, I get e to the x cosine y, plus some function which depends only on x, not y. Now, phi then has to match both of these criteria. So, well, I didn't write that down. So phi of x and y must be equal to e to the x cosine y. Sorry about that. My family just called me. Not having a cell phone, that doesn't normally happen during class. I'm not sure exactly what I was saying, so I'm going to double check here. Let's see, we had just done phi y. So we had found the second version of phi. Yes. So phi of x and y has to match both of these. So it has to have the e to the x cosine y that they both have. If there was a piece that this one had that this one didn't have, that didn't fall into that, it wasn't just like if this had a plus x, that would be fine because that fit with there, and we would put a plus x here. Now we could put like plus 2 because a function that depends only on x or y could be a constant, but that's what I meant when I said you get to pick any constant you want, so why not pick a 0? So this potential here, phi of xy equals e to the x cosine y works, and you can double check that if you want by just computing del phi. Right, if you compute del phi, then you're going to quickly get back to the f that we started with. So that's the process I use to find the potential. These are technically partial antiderivatives, right? Because phi x and phi y are functions of more than one variable. So I think that's kind of nice. We had partial derivatives before, now we have partial antiderivatives. And the difference between a regular antiderivative and a partial antiderivative is that we don't just get a constant, we get an unknown function of the other variables. Do another example of this. So for the function, for the vector field, sorry, f of x equals 2xy minus z squared, x squared plus 2xz, 2y minus 2xz, to test to see if this one is conservative. That last one, we only had an f and a g, so it was easier. You just used the first part of this test. But when we have an h, we have to check all 3 pairs. And I did these partial derivatives already, and feel free to pause and verify them for yourself. But fy equals gx, fz equals hx, and gz equals hy. And this might sound like it's a hard thing to remember, but essentially, like for gz equals hy. So here's g, there's h. G corresponds to the y, right? Like the y position. And h corresponds to the z position. And so I just am taking the partial of those with respect to their other variable. So g with respect to z, h with respect to y, those have to match. And so you can check those on all 3 of these. So once again, we have a conservative vector field. If one pair of these didn't match, it wouldn't be conservative, but these are going to be conservative so that we can find a potential. So Potential phi for this, we take the partial antiderivative of f, or phi x, or 2xy minus z squared with respect to x. We get x squared y minus xz squared, plus a function which depends only on the other two variables, y and z. We repeat this for g, take the antiderivative of g with respect to y to get another form of phi, and we get the x squared y, which matches. We get a 2yz, which doesn't match that, but we get an unknown function of just x and z. So you see, this, we don't know, it may not have everything, but we know that this part here, which isn't out here, that is contained in this C2, this function of just x and z. And similarly, this 2yz is contained in that C1 of yz. We've got one more partial antiderivative. We take h, we take the partial antiderivative of it with respect to z, and we get the 2yz again, we get the minus xz squared again, and then we don't have the x squared y piece, but we do have the unknown function of x and y. And so then we make it all matchy-matchy, and we say, well, I've got x squared y, and an unknown function of x and y, so that's this piece. I've got minus xz squared, I've got minus xz squared, and I've got an unknown function of x and z, so that's minus xz squared. And then I've got 2yz, and an unknown function of y and z, so that piece is there. So since this is conservative, this will work. If it's not conservative and you try this, something won't work out. You'll get some piece in one of these integrals that isn't in the others, and it could go wildly wrong, or there's a few sneaky problems in your homework where it's almost right. So watch out for that. All right, so the reason why we care about conservative vector fields is if our vector field is nice, if it is conservative, also continuous, that's just so that we can do a line integral over the vector field. But if we have a conservative vector field and a curve in that same region where our vector field exists as continuous and conservative that connects 2 points, so any 2 points A and B, then we can evaluate the line integral of f over c, any of those c, as phi of b minus phi of a. And this is the fundamental theorem of line integrals. And it kind of means that phi behaves like an antiderivative of f. If you want to think back to Calc 1, right? Calc 1, we had the fundamental theorem of calculus part 2, and so we had the definite integral of f of x dx from a to b was equal to cap f at b minus cap f at a, where f was any antiderivative of little f. And what we have here is very similar, right? We have, except now our cap f, right, is del phi. And remember that del, the gradient operator, back in chapter 13, that behaves a lot like our first derivative. And so in that regard, then phi, the potential, is like, I'm not saying it is, but it is like an antiderivative. For f. So that's why we care about it, is we get this nice fundamental theorem-like result. And that actually, it gives us a few things. By the way, the abbreviation is FTOLI, which I have read Fitoli for a long time. So if you ever hear me refer to Fitoli, I'm referring to the fundamental theorem of line integrals, this guy right here. So an upshot of this is that the line integral of f over c won't depend on the curve c if f is a gradient field, but only the start and end points a and b. And so we say that that line integral is independent of path, or we talk about path independence. This happens in a conservative vector field. This is why, by the way, if you have, you know, back in, high school, this is a table, by the way, it's not a pie, it's a table. If you have an object, a block sitting on the table, and we take and we move it around, and then we pop it back down in the same spot, the work done, remember work, equals f, the integral of f dot dr over c, there's my path c. If I start and stop it in the same place, then b and a are the same, and that would be phi of b minus phi of a. But this is only true because the field that we're moving it in is a conservative vector field. It's a gravitational field, which is a kind of radial field. And so radial fields have look something like this. F equals minus x minus y, maybe divided by the square root of x squared plus y squared. I think usually we square that. So negative x over x squared plus y squared, negative y over x squared plus y squared. That is really fuzzy, sorry about that. Maybe if I switch my pen. And so if I take fy, that's equal to negative 2xy over x squared plus y squared squared, right? And then, trying to remember, it's to the minus 1, that might be a plus. If I take gx, I get the same thing, though. I'm going to get 2xy over x squared plus y squared squared. So gravitational fields, any constant multiple of this isn't going to change the fact that these guys are equal. And even if I did something like cube this, or if I messed around with it in some other way, we're still going to get that these guys are equal. And so you have the gravitational fields are conservative. And that's why all through high school physics, we just told you that work did not care about lateral movement, but only a return to its elevation, because that's essentially what you're caring about in a gravitational field, or at least a standard gravitational field of one body. I'm not doing serious physics here, guys. All right, let's do an example. So we've got a potential and we have a gradient field, and we want to find the work done, or find the line integral of f over each of two curves. The first curve, both of these curves are going to go from the point 1, 0 to 0, 1. And we know f is a conservative vector field, but we've got two different paths. And I'm just going to show you here that this is path independent. And I'm going to show you the hard way. So the first one, this is a quarter circle, right, that starts at 1, 0 and stops at 0, 1. And this parameterization, C2, is a line segment that starts at 1, 0 and stops at 0, 1. And here I've just verified that the start and stop points are the same for both of them. So according to Fitoli, these should be equal because it doesn't matter which curve I use. is my vector field is continuous and conservative over all of R2. So I can just take f of b minus f of a, which is going to be, not f, phi of b minus phi of a. Well, phi is x squared minus y squared over 2. So this will be negative 1/2 minus 1/2, which is negative 1. But I'm going to do it the long way. I'm not going to do all the steps, but I'm going to set it up according to 15.2. So on C1, t goes from 0 to pi over 2. F with r of t plugged in is cosine of t, negative sine t. R prime of t is negative sine t cosine t. And when we do that dot product and then do that integral, we get negative 1. And finally, if we did it for C2, then here over C2, t goes from 0 to 1. F with r of t plugged in is 1 minus t, negative t. R prime is negative 1, 1. And when we do that dot product and do that integral, we get negative 1 again. So just verifying what we're talking about here. Then I wanted to do one more example. This is off an old exam. And here we're going to use the other notation for f dot dr, but that's just f equals yx and dr equals dx dy. So then that's just the dot product written out there. So calculate the integral over c of y dx plus x dy, where c is the part of the parabola y equals 2x squared from 0, 0 to 2, 8. And this was an exam problem, and you could do it by just parameterizing the curve. A lot of people did that. But it was actually really easy to do if you recognized that yx is a conservative vector field. Fy equals gx, they're both 1. And so phi is an antiderivative of y with respect to x, or I can look at it as an antiderivative of x with respect to y. Either way, the nicest phi to pick is just xy. Like I said, you could have a plus 5 or a minus pi there, but it doesn't change anything. And so then the line integral over c of y dx plus x dy, I just wrote it out in f dot dr form here, so yx dotted with dr, is equal to phi at 2, 8 minus phi at 0, 0. Remember, phi is just xy, so phi at 2, 8 is 16, and phi at 0, 0 is 0, and so this is 16. It's not a lot longer on this one if you parameterize the curve, but it is there are extra steps that you have to go through, and this is actually the shortest and nicest way to do it. And so this begins the first of our exceptions. So up till now, we took a look at our line integrals, and we said, okay, if the line integral is a scalar line integral, we use one formula, and if it's a vector line integral, we use a different formula. And those are both definition formulas. But now we are starting to get exceptions, and we're going to get two major exceptions. And the first is, if your vector field is conservative, then you can find the potential and use the fundamental theorem of line integrals. And that is almost always faster than parameterizing and using the 15.2 definition. So that's it for 15.3. See you guys later.